Hi, my name is Vyom, and in this video, I'm going to dive deep into PyTorch internals like strides, shapes, and views. Data is the bedrock of modern AI systems, and it's extremely important to understand and know how this data is actually represented in computers. The intended audience of this video is almost anyone who writes code in PyTorch or NumPy. This can be beginners all the way to professional ML researchers or engineers who just want a refresher on the topic. So now I can make four concrete promises to you. And by the end of this video, you will be able to look at a tensor operation and immediately say uh, if this operation is free or expensive. Two, if this operation will trigger a memory copy. Three, you will be able to answer if how the data is actually laid out in memory. And four, you will be able to answer what is the optimal way to reshape a particular tensor. Okay, so now first, let's just understand what a stride is. So let's say I have a PyTorch tensor. Um, let's say I have six elements. And now this is how this tensor looks like. It's just uh, six elements in this 1D array. Now, let's say I have another tensor y and I reshape x. So reshape is just I am taking this 1D array and I am, let's say, reshaping it into a 2 by 3 matrix. So what this means now is that y actually references the same memory as x, but y is just a 2 by 3 matrix. It's just a 2D matrix. Um, so we can confirm that both x and y point to the same location in memory, and we can do that. To verify, yes. So both the pointers of x and y point to the same part of memory. So now let's just look at the shape of x. Shape of x is just it just has one dimension of size 6, and y has two dimensions, and it is of size 2 comma 3, which means that it has two rows and three columns. Now let's take a look at what the stride of x is. So basically, let's first define what a stride is. So a stride is simply how many steps do I need to take in memory to get to the next element in each dimension? So since X only has one dimension, um, in order to get to the next element in X, I just need to uh, go to the very next element in memory, and hence the stride of X is one. I just need to advance by one to get to the next element in this 1D array. Now let's take a look at the stride of y. So what this tells us is that the stride of y is 3 comma 1. Now, does that actually make sense? So let's take a look. So when it comes to y, we have two dimensions. You can think of it as two dimensions. So you have the rows and the columns. So 0 comma 1 comma 2 is a row, and 3 comma 4 comma 5 is a row. And the columns are 0, 3, 1, 4, and 2, 5. So now, since the stride of y is 3 comma 1, what this means is that in order to get to the next element in the first dimension, or to get to the next row, I would need to advance by 3 steps in memory. Now, this actually does make sense because if I am, let's say, at 1 here, Since both of them are reference the same memory and memory is 1D, we can take a look at both of the views simultaneously. So let's say we're at 1 and we want to get to the next row. So we want to go from 1 to 4. How many steps do we need to advance? So what this tells us is that 1 and 4 are 3 steps apart in this 1D memory. Um, so this is what the stride of y represents in the first dimension. It is 3. And basically, it is just the size of a row. So in order to get to the next row, you need to advance by the same number of elements as the size of the row. And similarly for the stride in the second dimension, what this tells us is that we're at let's say we're at 0 and we want to get to the next column. So the next column um, is essentially just 1. So you want to get from 0 to 1. How many steps do I need to advance in 1D memory in order to get to the next column? And that's just simply 1 step. Hence, this is why the stride of y is 3 comma 1. And now, just for practice, we will also take a look at a stride of a 3D tensor. So let's say we have 24 elements, and um, we reshape X into a 3D tensor of size 2 comma 3 comma 4. So this is how Y looks like. Um, So basically, one simple way to actually visualize this is to actually understand what each axis or dimension represents. So basically, you can one intuitive way to think about this is that okay, like we have 4 columns over here, and we have 3 rows, and we actually have 2 copies uh, of a 3 by 4 matrix. So at the most common use case for 3D tensors in practice is let's say you have a data set of images. So you can think of Y as a data set of 3 by 4 images, and we have 2 images in this data set. Um, yeah, and we have 4 columns, 3 rows, and two instances in this data set. Now let's take a look at the stride of y. Now the stride of y is 12, comma 4, comma 1. Let's take a look and just do a sanity check of these numbers. So actually, let's start uh, from the last dimension. So in this case, it is 1. So what this means is that in order, if I am at a point, let's say 6, and I want to move uh, to the next column, then I just take 1 step in memory. So if I want to go to 7 from 6, I just I just need to go 1 step ahead in memory, which makes sense when you take a look at the truest form or representation of this 3D tensor in memory. So if we are at 6, in order to go to the next column, which is 7, we just advance 1 step. Now the second dimension, the stride of the second dimension is 4, which means that in order to go to the next row, I need to advance um, 4 steps ahead in memory. So let's say we're in the first row, so 0, 1, 2, 3, and we're at 0, and we want to go to the next row. We just advance 4 steps in memory. So we go from in order to get to 4 from 0, we just go 4 steps. So 1, 2, 3, 4. And now uh, the stride of the first dimension says that, and again, like the analogy that I mentioned about a data set of 3 by 4 images, I think will really come in handy here. What the stride of y, what the stride of the first dimension is saying that uh, is that how many steps in memory do I need to advance to get to the next image to get in the next 3 by 4 image. So since each since the size of each data in the data set is 3 by 4 or 12, we need to take 12 steps in memory in order to get to the next instance or to get to the next data point. Now this makes sense when you look at the 1D memory. The start of the first instance of data, or the start of the first data point, is at 0, and the start of the second example or data point is 12. So we needed to advance 12 steps in memory to get to the next example or the next data point. So you can almost think of strides as a coordinate system or a GPS for the underlying memory. So a stride will tell you how many steps do I need to advance in 1D memory to get to the next point in that dimension. And also another key insight is that whenever you are trying to understand tensors or tensor operations, it is often a good idea to take a look at these tensors, both in terms of the memory 1D view and also the logical view, which oftentimes is a multidimensional tensor. And now, in order to solidify our understanding of strides, we will just take a look at two more examples um, of how strides look like when we perform various tensor operations. So we will take a look at um, a tensor which has 6 elements, and let's say we reshape this tensor to be of size 2, comma 3. So this is how y looks like. We already saw this above. Now, let's say we want to take the transpose of y. So let's define z to be y transpose. So yeah, z or z is a 3 by 2 matrix, which is the transpose of this 2 by 3 matrix. Now, what you will notice is that both all three of the pointers. So we can print these pointers. So let's print the pointers of x, y, and z. And you'll notice that all of these pointers are equal, which means that both x, y, and z actually correspond to the same underlying 1D memory, but they're just different views of the underlying 6 element uh, 1D array or chunk of memory. And this is really important, and this is really interesting. Um, Now let's take a look at the strides of X and Z. So we already know what the stride of Y looks like. We saw this above. It's 3, comma 1. And now let's see what the stride of Z is. So the stride of Z is 1, comma 3. So what this means is that let's uh, let's also show the underlying memory view of Z, which is just the 1D tensor X. and this is Z. So basically, what a stride of 1 comma 3 means is that in order to get to the next row, how many steps in memory do I need to take? So the rows of Z are 0 comma 3, 1 comma 4, and 2 comma 5. So let's say we are at this element, we're at 4, and we want to get to the next corresponding element in the next row. So we want to get to 5 from 4. Um, the stride tells us that in order to get to the next row, we just move one step in memory, which makes sense when you take a look at both the memory view and the logical view. And now the stride of the second dimension of Z essentially is talking about how many steps in memory do I need to go to get to the next column. Now, we can see that the the columns in Z are 0, 1, 2 is the first column, and 3, 4, 5 is the second column. So in order to get from this first column to the second column, we need to set an offset of 3. So in order to get to 5 from 2, we go 3 steps in memory. In order to get from 1 to 4, we again go 3 steps, and the same to get uh, from 0 to 3. We just take 3 steps in linear memory. So I think by now you would have started to get a hang for what strides are. So let's take a look at another example. So let's say if we have Y, which is a 2 by 3 matrix, and YP or Y prime um, is Y, but let's only take alternate columns of Y. So we take all rows, but alternate columns. So the way that we do that is you go from the start column to the end column, but in steps of 2. Now, Y prime, let's just take a look. Yeah, it is a 2 by 2 matrix, and we have skipped uh, the 1, 4 column, and we only have the first column and the third column, or the column index 0 and the column index 2. So let's take a look at what the stride of Y prime is. Okay, so the stride is 3 comma 2. Let's analyze this by taking a look um, at at the underlying memory, but in both the logical and the 1D view. Um, so okay, yeah. So basically, what a stride of 3 comma 2 tells us is that in order to get to the next row, which is the first dimension, we advance 3 steps in memory, which means that in order to get to 5 from 2, we go 3 steps in memory, uh, which is correct um, when we take a look at this view. And now, interestingly, the stride of the second dimension is 2. Till now, we only saw strides of 1 for the last dimension. So now the stride of 2 tells us that in order to get to the next column, we actually need to take 2 steps in linear memory. Um, and that is correct because we are skipping alternate columns. Um, so let's take a look at the the tensor. So in order to get to the next column, so in order to get from 0 to 2 and from 3 to 5, we need to skip or we need to advance 2 steps in memory. So yeah, you can see that this passes the sanity check when we take a look at the underlying memory, which is the original X tensor, which is a 1D tensor containing 6 elements. Um, and so the interesting sort of conclusion here is that both Y and Y prime are simply just interpretations or views of the original underlying tensor X. And the way that we determine these views or interpretations is using strides. So, in order to interpret the same 1D tensor in the form of a 2 by 2 matrix, you would use a stride like 3 comma 2. And in order to sort of reshape or review the underlying 6 dimensional tensor in the form of a 3 by 2 matrix, you would use a stride of uh, y, which is 3 comma 1. So both y and y prime are they are referencing the same underlying memory, which is really interesting. Now that we've taken a look at strides, let's understand what row major order is. So, row major order is a convention to store multi-dimensional matrices or arrays in memory. And essentially, again, we saw this when we spoke about strides, but in Python and C, we follow the row major order convention, which essentially means that all of the rows are laid out consecutively in memory. So, for example, if we take a look at X, which is a 6 element tensor, and Y um, is a 2 by 3 view of X, Y is actually uh, in row major order, which means that um, all of the rows of Y are actually laid out consecutively in memory. So basically, what this would mean is that if we have a 2D matrix, for the sake of um, generality, let's consider arbitrary numbers A, B, C. Um, let's say we have a 2D matrix which looks like this: D, E, F. Now, in row major order, uh, we we get that all of the rows of this 2D matrix are laid out consecutively in memory. So the way that this would look like in memory is A, B, C, which is the first row, and then the second row, D, E, F. And um, just like we have the row major order, we also have another convention, um, which is followed in Fortran, not in C and Python. So I don't want to confuse things here, but basically, there is another way to store 2D matrices in memory as well, which is called the column major order. And this convention is followed in Fortran. Um, but basically, the way that this 2D matrix would be laid out in memory in column major order is that all of the columns would be laid out consecutively in memory. So the way that this would look like is that you have A and D, which is the first column, B and E, the second column, and C and F, the third column. So this is how this is row major order, um, which is what we have in Python and C. So this is what we actually need to understand and consider. And this is column major order, primarily uh, uh, the most um the most notable example is Fortran. And one more thing that we need to talk about when we mention row major order is is basically how we access elements in this 2D or more generally a multidimensional matrix representation. So let's say we have this 2D matrix, and let's say we want, let's say we call this example. Now we want the I comma j element in this 2D matrix. So the the way that we would do that is we want to find the offset, or we want to find which element in memory this 2D referenced element corresponds to. So in the I comma jth position of this matrix, which element would be laid out in this position. So the way that we would do that, and here I am assuming that I and j are within the bounds of the matrix. So the way that we would do that is I times the row size of the matrix plus j. Um, so for example, let's just take a look at a concrete example. Let's say 10, 11, 12, 13, 14, 15. These are the rows. Let's say we want to take a look at the element in the first row, but the third column. The way that we would do that, um, so this is 12. Now, this actually corresponds to if we strictly consider the row major order, um, which is this, or this is how it looks like in memory. We would get that this would be the size of the row in this example is 3. So this this would be the index, the 1D index of 12 in memory, and this actually corresponds to the index 2. And let's say we uh, let's say we want to verify. I mean, this the element at index 2 is 12. It is correct, but just for the sake of completeness, um, just want to do this. So yeah, um, both of these are equivalent. So this is basically how you convert this 2D coordinate into a 1D coordinate, which you can then directly reference in memory. And so this would be so yeah. So this would be essentially I times the row size, which is 3 in this case, plus 2. Now, another way to actually interpret uh, the um, this expression is actually in terms of I and j, which are the 2D coordinates, and the strides of this tensor. Now, one way to look at this is, okay, this is I times 3 plus j times 1. Now, the stride of example, um, sorry, yeah, so say convert this to Pytorch tensor. The stride is 3 comma 1, which is exactly the coefficients that we use in order to multiply this 2D coordinate. So uh, basically, what this means is that whenever we have in Python, in PyTorch, and in C, whenever we have a 2D matrix or a multidimensional matrix, but for this example, let's just consider we have a 2D matrix, and we want and let's say we have a 2D coordinate I comma j. In order to find where which element in memory references this coordinate, we would simply just uh, take take the 2D coordinate and apply a set of coefficients, which is just the stride. So example, let's just consider, okay, stride of stride of the first dimension. Uh, we add j times the stride of the second dimension. So that's how we can represent this in terms of strides as well. And now that we have understood how these tensors and multidimensional matrices are stored in memory when we use PyTorch, this actually tells us um, the way that these operations would work within the constraints of modern computer architecture. So whenever we have these large tensors of data, we know that we know based on these explorations that this data would be loaded row by row, and that is why the cache would have these elements in the form of consecutive rows, and hence doing row-based operations would be much more efficient than doing operations that involve multiple rows, because that would mean more trips to the cache. So, and this is particularly important when we consider really large multidimensional tensors and arrays. Okay, so now we're well positioned to understand um, how to determine whether a tensor is contiguous or not. And by contiguous, I am referring to uh, contiguousness in memory. So let's refresh the slate and let's take a look at this example where we have X, which is our six element 1D tensor, and Y is just a view of this 1D tensor in the form of a 2 by 3 matrix. So this is just the same underlying memory as X, but just um, represented by or represented as a 2 by 3 matrix. So yeah, this is how Y looks like. And we know that Y references the same memory as X. And one thing that you might ask yourself is, okay, we know for sure that X is laid out contiguously in memory. So whenever we define or whenever we initialize a new tensor in PyTorch, it is by default laid out contiguously in memory. And now the reshaping of X into a 2 by 3 matrix doesn't actually change anything in the underlying memory. It is just an alternate way to represent or take a look at the same underlying memory. So Y in this case, which is a 2 by 3 matrix, um, it references the same underlying memory as X. So intuitively, um, it should be clear that Y is also laid out contiguously in memory because we're not actually changing anything in the underlying data. And all of the elements of Y in row major order. So the row major order for Y would be 0, 1, 2, 3, 4, 5. So this representation of Y in row major order would be the exact same way that this tensor is actually represented in memory. So it is by definition contiguous. So this should give us true. Okay, that is logical. And now let's take a look at the transpose of Y. So let's say we have Z, which is the transpose of Y. Now, I think maybe you can stop and ask yourself whether you think Z is contiguous or not. And the way that you can think about whether a tensor is contiguous or not is if you represent a tensor in row major order, it would be the same way that the tensors are actually represented in memory. And the way that we know that that Z is actually represented in memory is it is represented in the same way. It is represented as a 1D array or tensor laid out like this: 0, 1, 2, 3, 4, 5. We know that again, Z is also just a different view of the same underlying memory, which is referenced by X. So Z is, but the way that Z is laid out, okay, so like we spoke about two ways of viewing a tensor, which is the memory view, which is, like the 1D view of how it's laid out in memory, because we know that memory is one-dimensional, and the logical view. And the logical view is simply how we represent this 1D memory um, when we reshape and convert this into multidimensional tensors. So this is the logical view of Z. And the way that we determine if Z is contiguous or not is if the row major order of the logical view of Z equals the row major order or the actual way that it is represented in memory or not. Now, according to the logical view, Z in row major order would be represented in in this form where consecutive rows are stored together. Now, this row major order representation of the logical view of Z, um, this actually is not equal to the way that the underlying memory that Z references is laid out. Because the way that it is laid out is in the form of 0, 1, 2, 3, 4, 5. So this should give you an indication. Uh, yeah, no. So this should give you an indication that Z is not contiguous. So if um, Z is contiguous, so yes, Z is not contiguous. This is false because of this reason that the row major order representation of the logical view of Z is not equal to the way that it's actually laid out in memory. And now that we've taken a look at this example, I would just like to touch base on one more example of y prime. So this is what y looks like, and let's define y prime as we have before to be y, all the rows of y, but alternate columns of y. And this is how y prime looks like. Um, Now you can pause and ask yourself if y prime is a contiguous tensor or not. Um, um, let's see. What do you think? Um, I think this should be fairly intuitive that the row major order of y prime is actually not the way that the underlying memory is laid out. Because y prime again just it references x, and x is a 1D tensor, which is laid out like one. It is laid out like this: 0, 1, 2, 3, 4, 5. And the way that we have defined y prime actually involves uh, skipping alternate columns. So by definition, y prime should not be contiguous. And that indeed is the case. So again, I think one of the common ways that you can make a contiguous tensor non-contiguous is one simply transposing uh, or taking the transpose of the tensor and any sort of slicing operations which involve taking a subset of all of the elements of the original tensor. So these are some of the most common ways to actually make a tensor non-contiguous with reference to the way that it's actually laid out in memory. So now, going back to the four original goals of this video, I think we I think we now have a very good understanding of how these tensors are actually represented in memory. So I think one of those goals has been accomplished. So we can now move on and explore some of the other topics. Actually, before we move on, I think it would be a good idea to do a quick summarization of the key ideas that we've discussed so far, uh, especially when it deals with contiguousness and strides. So I will be linking these notes in the YouTube video description. Um, but let's take a look at this right now. So basically, we can actually do a contiguousness check using some alternate ways and approaches as well. So one of these is a tensor is contiguous only if the strides decrease from left to right. So when we examine the contiguous tensors that we've seen so far, okay, let's just refresh the slate. Let's say I have um, a tensor um, that is of shape 2, 3, 4. The stride of this contiguous tensor is 12, 4, 1, and this is in strictly decreasing order. So this satisfies this particular check. So decreasing strides are a necessary but not a sufficient condition for for a tensor to be contiguous. So that is important. Um, and a tensor is contiguous if its strides follow this particular pattern. So the stride of I equals the stride of the next dimension multiplied by the size of the next dimension. So concretely, when we look at the tensor A, the shape of this tensor is 2, 3, 4. So the stride at 0, so 12, should be equal to the stride of the next dimension, 4, times the size of the next dimension, 3. So this is this does match. So 12 equals 12. And yeah, and then yeah, I think we spoke about this. A tensor is contiguous if and only if its elements occupy a single block of memory with addresses that advance by exactly one element when visited in the canonical order for the chosen memory format, which is just a fancy way of saying the row major order, which is the default in Python. Um, and yeah, some of the key characteristics of contiguous tensors is the last dimension stride is always 1. Um, this actually should be intuitive because the last dimension, um, you should always be moving to the very next element laid out in memory because that is because this is the dimension where the fastest increase of the values happens. So yeah, this is also a necessary condition for contiguous tensors, and there should be no memory gaps. Elements follow each other without skipping memory addresses, which is what we saw when we took a slice of a contiguous tensor. We saw that there were these gaps in memory, which because of which y prime. is not contiguous. And there should be a predictable stride pattern. Each dimension stride is the product of all subsequent dimension sizes, which is also what you will observe when you examine the shape and strides. Okay, now we're going to touch upon the concept of views and reshapes, which again I think is one of the key topics and concepts in this video. Um, so views and reshapes can look very similar, but there is a subtle difference in how they actually operate in PyTorch. So both reshape and view are used to change the representation, the shape, or the form of a particular tensor. So, for example, we have already touched upon and seen um, how to use reshapes and views. So let's just refresh. So let's say we have a six element tensor. We can reshape this into 2 by 3 matrix. We can also uh, construct a view of X, which is in the form of a 2 by 3 matrix. And both of these are identical, but here is the subtle difference. Now let me define Y as a transpose of X. So now Y is sorry. Let me define Y as the transpose of the 2 by 3 representation of X. So Y should now be a 3 by 2 matrix. Uh, and let's see if Y is contiguous. Well, it is not. You should. Yeah, I think based on what we've discussed, I think you would know that it is not contiguous because this is not how it is. The underlying memory is laid out in row major order. So since Y is not contiguous, uh, so now let's try the reshape and view operations uh, on Y, which is not contiguous. Um, so this is how Y looks, and let's say I want to convert Y in back into a 1D representation. So the way that I would do that um, is using this notation where -1 just flattens Y out. So let's see if this works or not. Okay. So ideally, uh, let's assume for now that in a hypothetical universe, if Y was contiguous, then flattening it out into a 1D tensor would render this result. You would just flatten out the rows of Y. So 0, 3, 1, 4, 2, 5. This is the row major order representation of this tensor Y. So this result is clearly uh, not possible um, because the underlying memory is laid out like so: 0, 1, 2, 3, 4, 5. So essentially, if uh, the only way to get this 1D representation, which is characterized by Y, uh, by the flattening out of Y using view of -1, would be if I take this underlying memory and rearrange it uh, to be now of this form. So one important thing to note is that view does not support these rearrangements of memory. You can think of view as a constant time operation, which only involves manipulating the stride of the tensor to to achieve the view. On the other hand, um, you will notice that it is actually possible to reshape y. And internally, what reshape does is that if it is not possible to create um, this uh, this form of the underlying memory, then it simply just creates a copy of the memory that was referenced by the tensor that this reshape operation was applied to. And we can quickly verify that that indeed is the case. So the the memory that Y and Z reference is actually not the same. So yeah, so this is a critical distinction between views and reshapes. So view will simply throw a runtime error if you try to create a view that conflicts with the way that the underlying memory is laid out. Whereas, as we have seen from this example, that that the reshape operation is much more liberal, and if it is not possible to to simply manipulate the stride and create an alternate representation of the underlying memory rendered by the reshape, then it simply creates a copy of the underlying memory and completes the reshape operation on this new chunk of memory. So the bottom line is that a view operation is always it always runs in constant time, whereas a reshape operation could potentially uh, run in linear time if the underlying memory representation does not support the reshape, or if it conflicts with the row major order representation the of the reshape operation. So this is actually a pretty important concept while building ML models, and this concept of a reshape um, it could actually be the difference between a model that takes 8 hours to train versus a model that takes 2 hours to train, and a model that potentially can balloon up your GPU cost to thousands of dollars versus just hundreds of dollars. So this is actually extremely critical to understand the the underlying tensor that you are attempting to reshape. And yeah, I hope this example proves or shows you the underlying dynamics at play. And to hone this point even further, here is an example of these mechanics at play. Um, so I have defined this function, and what it does is that there is a base tensor of size 1,000 by 1,000, and we are essentially um, summing all of the elements of x in this loop. Because x is contiguous, we can take the view. This just flattens out x and takes the sum of all of the elements of x. And here is the non-contiguous case where we take the transpose of X, which makes this tensor non-contiguous. And we have the same loop, but instead of the view operation, we have the reshape operation, which is much more liberal and which creates a copy of the tensor if 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 there are any conflicts or if the underlying tensor is non-contiguous. And as we will see, let's just run this function. Um, what we will see is that the non-contiguous case is actually 12 times slower than this contiguous case, which makes use of the views. And this is extremely critical when it comes to when you scale this example to a much larger um, and uh, and a much more uh, a critical case where you're dealing with extremely large tensors and the operations are costly. And if you are doing reshapes on non-contiguous tensors, then it could potentially be a lot more inefficient um, uh, if as opposed to doing the operations on contiguous tensors. So now that we have covered most of the conceptual points, let's actually take a look at some exercises which will test our knowledge of these concepts. So yeah, here I have the code for exercise one. We basically have this 4 by 6 tensor, and we need to predict whether these reshape operations render views or copies. So, okay, in test case A, we are essentially reshaping a 4 by 6 tensor to a 2 by 12 tensor. So, yeah, it should reference the same data because even in when we simply create a 2 by 12 representation of this tensor, all of the elements would would still be in the correct row major order as all of the elements that are laid out in memory. We can quickly see that. Let's just take a uh, let's just see this in action. So we have this tensor X. This is the row major. So it's actually laid out in increasing order 0, 1, 2, 3, 4, 5 till 23. This is how it's laid out in 1D memory. Um, Even when we reshape X into a 2 by 12 tensor, it in row major order, when we lay this tensor down, it would be laid out in consecutive rows. So again, it will go all the way from 0, 1, 2 till 11, and then from 12 to 23. So this the row major order representation of this tensor actually does not violate the actual representation of this tensor in 1D memory, and hence this we can simply do a reshape by manipulating the strides rather than copying over the data. So this is reshape A is a view of the original tensor. And when we consider reshape B, this would also be just a view because um, yeah, the row major order of this representation also does not violate the way that it's laid out in memory. So this case would also be a view. And here, this is when things get interesting. If we take a transpose of X, now suddenly the transpose is it's all jumbled. The row major order of this transpose is actually not the way that it's laid out in 1D memory, and any sort of reshape operations on this transposed tensor um, will not um, will not will actually conflict with the way that is laid out in memory. So again, when we reshape the transpose, we get this 8 by 3 matrix. This the row major order of this 8 by 3 matrix clearly violates how it's laid out in memory. So um, this will be a copy. Okay, so let's see if this actually uh, matches what we get when we run this function. Okay, so here the original tensor is contiguous, um, and when we do a reshape, the actual memory is conserved, so it is the same data. Even the test case B, the reshape, it does not conflict with the underlying data. Now, when we actually do the transpose, we suddenly get a tensor that is not contiguous, but that it still references the same underlying memory, but just using a very specific stride of 1 comma 6. Now, when we actually reshape this non-contiguous tensor, this actually violates the way that the underlying memory is represented, and hence this reshape will actually trigger a copy, and we can see that this is actually not the same data as the transposed tensor. So this points to a different um, memory chunk. So these two are not equal. So yeah, great. So this confirms our initial predictions. Let's move on to the next exercise. Okay, so this is exercise two. So I'll just talk a little bit about what this permute operation corresponds to. Basically, permute just swaps the strides, the underlying tensor. So in this case, if we have this tensor, the x has a specific stride. If we take a permutation of x, and let's say we swap the strides of the first and second dimensions, then the stride of y, um, then the stride of y is just the swapped strides of the original tensor. And this is what the original tensor looks like. This is the permuted tensor. Now, the the key insight here is that Y is actually not contiguous because its row major order conflicts with the way that the underlying tensor X over here, uh, this this tensor is stored in 1D memory. So because of this conflict, um, we get that Y is not contiguous, but it still references the same chunk of memory, but just using a different stride uh, into the underlying memory. So now so the permutation operation is straightforward in that it just swaps the strides of the permuted configuration of the tensor. So in this case, the original tensor has a stride of 12 comma 4 comma 1. So when we take this permutation, we get that the strides would be swapped. So we have 4 comma 12 comma 1. Um, and similarly, when we do this permutation, we essentially are taking a reverse. So the strides will now be in a reverse of the original stride, so 1 comma 4 comma 12. And in the last test case, we are basically swapping the first and the last dimensions. So the strides will also be swapped in that order. So we should get uh, 4 comma 1 comma 12. So let's verify if this is the case. Um, yes. So yeah, this basically confirms our predictions for exercise 2. Okay, now I promise this is the final exercise in this video. So here we will be predicting if these operations will work or not. So basically, all of the operations that we are performing here are views. Um, we know that if a view creates a representation of the underlying memory that conflicts with the way that it is actually represented, the view will throw a runtime error. So we need to predict if indeed that happens here or not. Okay, so let's take a look at uh, the context. So X is a 4 by 6 tensor. Um, we now create a view of X of shape 2 comma 12. This should work, as we have seen. So this just lays it out in row major order, but in a different view or a different transformation, but it still preserves preserves the row major order representation. Now, when we take the transpose of X, we suddenly have a non-contiguous tensor in X transposed. Um, and then when we take the view of this tensor, um, let us see what happens. I think, yeah, so this should not work because, um, okay, let's just work this out. So here, this is the context. We take the transpose of X. So that's X, and this is X transposed. X transposed is not contiguous, and then now we want to take a view of this transposed tensor. Yeah, this will not work because in order to take a 2 by 12 view of this 6 by 4 matrix, you would have to lay it out um, in something of a similar form. So here you would actually the way that you would do this, if it was theoretically possible, or the way that a reshape would actually do this is it would convert this 6 by 4 matrix into row major order uh, to get a 1D tensor, and then you convert that 1D tensor into a 2 by 12 view. So you would get something that looks like this, and so on. Each row would just have these elements that um, that are laid out like so. Let's just see what would happen if we take a reshape instead of a view. And sorry, by 2 by 12, it's actually two rows and 12 columns. So basically what this would do is that it would lay this out in row major order, and then you would essentially convert that to a 2 by 12 tensor. And the way that you would do that is each row now would have uh, three rows of the original underlying tensor. So you would you would group it in batches of three to give you this. And but clearly, a view would not be possible in this case because if you take a look at what is happening under the hood, uh, the row major order that renders this 2 by 12 uh, tensor actually violates the way uh, that the memory is actually laid out um, in this underlying uh, tensor X. So essentially, since there is a conflict, you would have to create a copy of the memory and lay it out in in a 1D representation that allows such this particular logical view to actually materialize. So basically, this view will not work. Um, and now this is a really interesting case in my opinion. And I think like this is again, these concepts are not as straightforward as one might expect. So like you really have to understand how the memory management actually works in order to answer this question. And this is tricky, but I think once you truly understand how the underlying memory works, then then I think you wouldn't be confused about this. But this test case C is actually a little bit confusing, and we will see why. So let's just get a clean slate here. So let's assume we have X, which is this tensor. Now we are, again, we take every other column of X. And now this actually renders a non-contiguous tensor. And now let's see and try to predict if this view is actually possible or not. So, okay, it is possible, and let's understand why. So, basically, what view of C looks like is we're flattening X slice out into a 1D tensor. You can think of this similar to -1, but let's just keep it to 12 for now. And we see that, okay, this is laid out like so. It contains alternate elements in the underlying tensor. If we actually take a look at what this looks like, let's say we have X here. So let's take a look at what X looks like before the reshape to get an understanding. So this is how the underlying tensor is laid out in memory. It's just 0, 1, 2, 3 till 23. And here the view of C is actually just alternate uh, elements of this 1D tensor. But if you see, this actually still, it does not violate the row major order representation. Or another way to think about this is that we, uh, so the reason why this view is possible is that you can take the underlying memory, which is X in this case, and apply a stride to it to render the view. So it does not actually conflict with the way that this is represented in memory internally. Even though we know that X slice is not contiguous, uh, but uh, yeah, and the stride that we use uh, in order to take this underlying memory and represent it using uh, and represent it as this is simply to take a stride of two. And if we see what the stride of view underscore c is, we should get two. So let's take the stride. Yes, and this is two. So basically, what this means is that uh, we when we apply this stride to the underlying memory, that is when we get this view. So there are no conflicts. So this is a subtle yet very instructive case where you don't strictly need these tensors to be contiguous for us to render a valid view. It is the thing that you need to actually think about is that if this view uh, can be constructed by applying a stride to the underlying memory. If there are no conflicts and if a stride can be applied to the underlying memory to get this view, then this view is possible. And so in this case, this should be possible. Let's actually run this to verify our findings. Well, we already have, but still for the sake of completeness. Yeah, we see that since this code has run without throwing any errors, uh, these operations. Okay, my bad. I just need to make sure that all of these operations succeeded. So yes, view C has succeeded. View B has failed, and we correctly predicted that it should not be possible to create view B, so no in this case. And view A should be what should have succeeded. Yes. So this confirms our findings. So yeah, I think that's it. I think you now should have all of the tools and the knowledge to understand exactly how memory is manipulated in PyTorch and using various common tensor operations. And I think a strong knowledge of this is really valuable when you're building ML models in production and knowing what operations are O of n. So typically, you want to uh, you don't want reshapes that cause copies because this will slow down your code. You always want tensor manipulation to happen in constant time by just changing the strides and not actually creating copies of the underlying memory. So that's it. Thanks for sticking by, and I hope this helps. And also, I will be sharing the links to all of the code that we worked on in the description of the video. Thanks a lot, and see you soon.